Okay, we're going to do hydrogenation of dienes. So I just want to touch base on this. Dienes are double bonds, but you have two. So 1, 2. So it's di, 2, ene, double bond. Okay, so stability of alkenes. First, we have this series of alkenes, and then we have to say which ones are the most stable. So for stability of alkenes, we're going to go by the rule of the more substituted the double bond, the more stable it is. For example, you have carbon here, carbon here. How many substituents do you have in this one? 1, 2, 3, 4. Opposed to this one, where you have carbon here, you only have one substituent. So in all of these, the most substituted one is C. So I will say C, which has 4. Then the second best would have to be E, which is 1, 2, 3. So I will say C is better than E, then which is better than, then you have 2 that have 2. 1, 2, and this one has 1, 2. So the only difference is that this one is trans, this one is cis. So if you go by conformation and steric hindrance, you know that this one is staggered and this one is eclipsed. So your staggered conformation is more stable than the eclipse. Then after that, you have the one with 1, which is B. So this is what it's going to look like once you order them. And then when you go to stability of dienes, you have these 3 types, which is conjugated. Conjugated is a system of double, single, double, single, double. And isolated, which you have a double bond and a double bond, and they're not conjugated. It's not a double, single, double. They don't even know that there's a double bond. This molecule doesn't know that there's a double bond this side. They work as alkenes pretty much. And you have your cumulated, which you have the 2 double bonds come out of the same carbon. That is terrible, stability-wise. So let's move on to the mechanism. We're going to use a conjugated system, double, single, double. We're going to do this one at low temperature, or 0 degrees Celsius. So what's going to happen here is the nucleophile, the double bond, is going to attack this partial positive hydrogen. And then Br is going to leave with the electrons. And we'll have it here, plus Br minus. And you have your double bond here that has not been touched. You form a carbocation. You're going to remember the most stable carbocation on this molecule should be in the tertiary position. So that's where you get it. Then I copy whatever is there. I copy it here, my formal charge. Then the Br minus is going to attack that positive center. And then this, at low temperature, what you get is a kinetic mechanism, and it's a 1-2 addition. You added a hydrogen to this carbon right here, which is the one that picks it up. I did not write my hydrogens. So you did pick up the hydrogen here, and then on the carbon right next to it, meaning 1, 2, you get your Br right here. So you picked up the hydrogen here, and then the Br on the carbon next to it. What happens if you do this mechanism at high temperature now? This is 40 degrees Celsius. You have the same exact molecule and the same reactant. So the only thing that you're changing is the temperature. But the change is drastic. So you have your conjugated system, you have the same initial step. Your nucleophile is going to attack the partially positive hydrogen. The Br is going to leave with the electrons, and this is what you're going to get. You're going to get a carbon in the tertiary position, and here you picked up a hydrogen. Plus Br minus. Then the second step, what I did is I grabbed this molecule alone, and here, and I did a resonance. This is what this arrow means. Double head arrow, you're just doing resonance. So what happens is this came here, the double bond, to stabilize the positive charge. So you have an empty orbital on this carbon now, which is represented by this positive, by the formal charge positive. And then I grab this one and I use it for the next step in the mechanism. So I have my positive center right here. I have my negative Br, which is going to attack the positive, and you get this one. So in this case, what we got was a thermodynamic product and a 1,4 addition. You have your hydrogen right here, which is the first addition. So if you count this one as your carbon 1, 2, 3, 4, in the fourth carbon you get the second addition. Now, the thermodynamic product, if it helps you remember, the thermodynamic product is the one that's going to give you the most stable alkene. You will have 1, 2, 3 substituents to this double bond. While if you go to the kinetic, you're only going to have 1 substituent to this double bond. Okay, so an example. We have 1,3 hexadiene plus HCl, and we're going to do it at 40 degrees Celsius. That means that we're going to have a 1,4 addition, right? So that's the product. So let's see how we arrive at that. I copy this part. And my conjugated system of double bonds plus HCl. And then I know that this one will attack the partially positive hydrogen. The chlorine is a good leaving group, is going to take the electrons with it. Then what happens is this carbon right here has 1, 2, 3 bonds. It has 1 hydrogen here that I'm not showing. Now it's going to pick up another hydrogen, so I will not show the 2 hydrogens there. And your carbocation will be right here, this carbon right here. Then your other double bond has not moved, plus Cl minus. Then what's going to happen is I will make a resonance of this one. So I have this structure right here, my formal charge, and then double-headed arrows. And I know I did not break any sigma bonds, so the pi bond is going to break, it's going to come to the middle to stabilize the positive center, and you will get your positive formal charge right here in that carbon. And your double bond went there. So what happens then is this plus Cl minus. So what's going to happen is negative goes to positive, and you get your 1,4 addition, which is the H here that I picked up and the Cl right here. So this, oh, and my double bond. So this is the same as that. So just for fun, let's do the 1, 2 addition. So I will pick up the same thing right here. My conjugated system, double, single, double, plus HCl. I know that this one picks up the partially positive hydrogen. Chlorine is a good leaving group, it takes off. So I get this structure right here. My H up there, positive right here, and the other bond didn't move. And then I pick up that molecule on this side, and my formal charge plus Cl minus, and I know the minus attacks the positive, and you get your 1, 2 addition right here. So this is 1, 2, and this is your 1, 4.